In this video, we're going to be answering one of the concerns that many students had when we did a review about the significance of atomic mass. So if we do a little bit of a review of the significance of all of the numbers in carbon's elemental data, we start obviously with the atomic number, which is the number that we use to identify the number of protons an element has, and also, therefore, the number of electrons that the element has before it forms an ion. Now, because we know number of protons and number of electrons, the last number that we need to calculate in order to get all of the data we need to draw an atomic structure is simply the number of neutrons, which, unlike the number of protons and electrons, is not actually explicitly listed. So instead, we need to take the atomic mass number, which we find at the bottom of the element symbol here, and subtract the atomic number from that, because the atomic mass number is simply the number of protons plus the number of neutrons, since electrons are assumed to have a mass of 0. And the step that we did at this stage is we say that 12.01 is approximately equal to 12. We would subtract 6 protons from that, and therefore carbon is assumed to have 6 neutrons. Now, the reason why this rounding is present is, well, is it possible to have 0.01 neutrons? Obviously, the answer is no, so the question then is, where did this extra 0.01 come from in carbon's atomic mass if fractional protons and fractional neutrons are not possible? Well, in order to answer that question, we need to talk about something that we call isotopes. So in chemistry, and indeed in any scientific field, whenever a word begins with the prefix iso, it tells us that we are looking at something that is the same. So an isotope is a form of an element, meaning that two different isotopes of carbon are both carbon, and we know that they are both carbon because each of them contains the same number of protons, but unlike the number of protons, which is identical, each different isotope will contain a different number of neutrons, and therefore the mass of one isotope is not identical to the mass of another. For example, there are actually two isotopes that both exist on Earth: carbon with an atomic mass of 12 and carbon with an atomic mass of 13. Now, if we were to look at the Bohr-Rutherford diagrams of each of these carbons, they would be almost indistinguishable in that both of these are carbon, meaning that they both have 6 protons in their nucleus, and because they would also have the same number of electrons before it formed a compound. The only difference then is the atomic mass. So if carbon-12 has a mass of 12 and 6 protons, that would mean that it has 6 neutrons in order to get an atomic mass of 12. But as we see, when we calculate the number of neutrons for carbon-13, we see that there would actually be 7 neutrons, which explains the difference in atomic mass between the two. So then why isn't the atomic mass number simply 12.5? Because that's the middle number in between 12 and 13. Well, the atomic masses on the periodic table are actually listed not as a perfect average between the two, but as what we call a weighted average, which naturally accounts for how commonly each of the isotopes exists in nature. For example, 98.89% of all carbon that exists on Earth exists as carbon-12, meaning it has 6 neutrons rather than 7, and the remaining percentage of carbon-13 would therefore be 1.11%, approximately speaking. Again, these are not exact, but are simply a collection of survey data that has been rounded. So these percentages that refer to how commonly you find each form of each isotope is what we call the percent abundance, which simply refers to how frequently or how common each isotope exists in nature. And again, by in nature, we actually mean on Earth. Now, using a weighted average calculation, what we can do is we can calculate the average or weighted average atomic mass and actually determine where the number 12.01 came from. And to do a weighted average calculation, all that we do is we take the atomic mass of each isotope and we multiply it by each of these percentages that we would express as a decimal. So 98.89% we would express as 0.9889. And then we add this to the atomic mass of all other isotopes multiplied by their percent abundances. So 1.11% we would write as 0.0111. And when we add, or firstly, when we multiply each of the atomic masses of each isotope by its percent abundance, you should find these numbers below. So 12 times 98.89% should come out to 11.8668, which we would then add to 13 times 0.0111, which comes to exactly 0.1443, and if we add these two numbers together, the average or weighted average atomic mass of carbon comes out to be 12.0111, and if we round this to 2 decimal places, this number comes to approximately 12.01, which you'll find is the average atomic mass that is listed for carbon on the periodic table. And now we know that the 0.1 does not in fact refer to 0.01 neutrons, but is a representation of what the weighted average of carbon's atomic mass is based on how commonly one isotope occurs relative to the other. To practice understanding this concept, you can try the practice problems below in which the weighted averages of each of the isotopes is listed below, and you know that you have done the calculation correctly if you find that your weighted average atomic mass comes out to being exactly or close to what is written on the periodic table.